This is the accessing the feasibility of deploying solar power underwater devices in water surrounding New York City. I'm William Rand.
I'm Christina Jiang, and this is today's video presentations overview. Our research objective is to determine the absorption coefficient of various water resources around New York City, and we're gonna deduct a graph like the right picture, and we're gonna analyze data for feasibility to use underwater solar panels. Solar energy collection in aquatic environment is promising for the deployment of solar-powered underwater sensors and communication devices, which could revolutionize environmental and oceanographic monitoring. However, identifying optimal solar technology for these applications is challenging because of the time and material costs of field deployments. So it's very limited by the lack of power sources, but underwater solar cells can use semiconductors with wider band gaps to increase the efficiency. For the materials, we use Carry 60 UV-Vis spectral photometer. It can measure how light goes through the water samples to calculate the transmittance. And our procedure includes we collect water samples every week, and then we do sample test. At last, we calculate the absorption coefficient. Here is our map to collect the water samples around New York City. We go from East River to the wider range until Jamaica Bay and Long Island Sound. Here are some pictures of the water samples: the East River, the Bowery Bay, the Little Neck Bay, Harlem River, Hudson River, and Long Island Sound.
This is the absorption coefficient of various water sources around New York City. And you can see here it displays similar trend as the previous slides, where it displays the absorption coefficient of one of the clearest waters in the world. As a result, this is the average radiance of all the water sources collected at 0.1 meters, and we have a maximum depth of 0.4 meters. The input power is 0.102 milliwatts per centimeter squared, and our output power at a maximum efficiency is 0.048 milliwatts per centimeter squared. Band gap at maximum efficiency is 1.71 electrovolts, and we have a maximum efficiency of 46.7%, allowing us to produce 46.7% of the light shine under the solar panels to be conducted into electricity. To conclude, our underwater solar panel is feasible as it can produce 46% of electricity, and it can improve data collection in aquatic environments because the sensor doesn't have to be recharged at a water surface every single time.